Hi, my name is Jay Lee from Texas Tech University, and I'd like to thank Cluster 2020 for giving me the opportunity to share our research with the community. My topic is MonSTer, an out-of-the-box monitoring tool for high-performance computing systems. This research is supported by Dell EMC and Intel through the NSF CSE program. And I would also like to give thanks to the colleagues and advisors in that intensive scalable computing lab. This is my agenda today. First, I will introduce the background and motivation of this research. Then, I will introduce the monitoring architecture and explain the design of each module. In the third part, I will focus on the evaluation and the experience learned from the production deployment. I will conclude my presentation with conclusions and future work. Let's first look at the background and motivation of this research. Monitoring the status of high-performance computing platforms is critical to the successful operation of these complex systems. The main activity is keeping track of hardware and software metrics. The monitoring metrics enables the administrators to troubleshoot problems and maintain the health of the system and to provide stable computing services for HPC users. We are all agree that accurate and fine-grained monitoring activities are needed in HPC systems. There are also open source or commercial tools proposed to address this need. However, it seems that these existing monitoring tools are inadequate to track the interplay between running jobs and HPC system in a timely manner. Here, I use a diagram to illustrate the features of these existing monitoring tools. First, as a primary feature, a monitoring tool should keep track of the system status such as CPU usage, CPU temperature, power usage, etc. Additionally, since the HPC facilities are mainly used by researchers and lots of scientific computing jobs are running on the platform, it is also necessary to monitor the running job status, such as how many resources it takes and how long it runs. And by correlating the job metrics with system status, it reveals insightful knowledge of the system. Another important feature is the monitoring tool should provide the metrics in a timely manner, which enables detect anomalies in time. The last feature that we think is important is usability. That is, the monitoring tool should be easy to deploy and can even be installed and upgraded without interfering the HPC system. There are some monitoring tools that are characterized according to their features. For example, Nagios is able to monitor the system status in a timely manner, but it cannot monitor job metrics. Conganier is also not able to monitor jobs metrics, and it is not easy to deploy. LDMS is not easy to deploy either. While the TACC status can collect and analyze the resource usage data of jobs, but since it writes the collected data into a text file and is aggregated every 24 hours, it does not support job monitoring in real time. Comparing to these existing tools, our proposal MonSTer is designed to monitor system status as well as job data in near real time. And it aims to be easy to deploy with little interference on the HPC system. Before we proceed, I want to briefly introduce two techniques that exist in the HPC system. First is the Redfish protocol. Many vendors have adopted this protocol in their server products. This protocol exposes an interface to access Baseboard Management Controller information through Redfish API, which allows out-of-band retrieval of hardware information and sensor data such as power usage, temperature, fan speed, etc. On the other hand, large-scale production HPC deploy Resource Manager to schedule applications across computing resources. Two of the popular resource managers are Univa Grid Engine and Slurm. The resource manager has the overall status of the computing resources and can allocate appropriate resources to jobs to achieve efficient scheduling. These status include CPU usage, memory usage of the computing nodes. It also includes the resources used by a job, such as how many nodes are allocated to this job and so on. This information are also exposed as APIs. For example, we can use Arc to access the UGE, and the Slurm 2002 provides RESTful API which allow clients to communicate with Slurm. MonSTer leverages these existing techniques to monitor the system by retrieving metrics from the provided APIs. It correlates collected metrics and reveals insightful knowledge of how platform components interact with each other without having additional overhead on applications and computing nodes. With that being said, in the following slides, I will talk about the design of MonSTer in details. In this slide, I will give an overview of MonSTer architecture. As we just mentioned, the data sources are nodes equipped with BMCs and the resource manager. The metric collector captures interesting data via the Redfish APIs and the resource manager API. This part is the collection module. The collected data will then be stored into a time series database in InfluxDB, where the data will be organized into a set of measurements. The measurements in time series database can be regarded as tables in relational database. This informs the storage module. Before the data is consumed by the data analytic tools, we have another layer called Metrics Builder. Its primary functions includes accelerating the data retrieval, correlating and aggregating data. Additionally, it exposes an API to consumers. The Metrics Builder is the aggregation module in our monitoring architecture. Our last component is a data analysis tool called HyperJobViz. It's developed specifically for visualizing and analyzing the correlation between job metrics and system metrics. Detailed functionalities of this analytical tool will be presented later. This is the analysis module of the MonSTer. I will present the details of each module in the following slides. In this slide, I will explain how metrics collector works based on the deployment on the 467 nodes cluster at Texas Tech University. The computing nodes are all equipped with Dell iDRAC 8 to retrieve the BMC metrics. The metrics collector calls the Redfish APIs and gets metrics through an independent network. This approach avoids perturbing ongoing computations across compute fabric and allows status to be obtained even if the computing node is down. In our experiment, one Redfish API request takes around 4 seconds, and asynchronous request for all supported metrics from all 467 nodes takes about 55 seconds. The resource manager in our cluster is UGE 8.5.5. The queuemaster daemon is running on the head node. The execution daemons are running on all computing nodes. These execution daemons periodically report the status to the queuemaster daemon at fixed intervals. The queuemaster daemon accepts incoming jobs, and based on the available computing resources, it dispatches jobs to execute. UG also has a component called ARCO, which is a web-based tool for accessing accounting information. Metrics collector uses ARCO to access computing resource metrics and application details. The collection interval is limited by the response time of the BMC and job scheduler state update time, which are 55 seconds and 40 seconds separately. Therefore, our current implementation keeps the telemetry data collected at a reasonable interval of 60 seconds to ensure that BMC metrics are retrieved and to collect resource manager metrics whenever possible. Here, I list some of the representative metrics obtained from the BMCs and the UGE. For example, in the BMC metrics, we have health information, CPU temperature, fan speed, power usage, etc. In the UG metrics, we have resource usage info, such as CPU usage, memory used. Some job-related info are also included, such as username, job ID, submit time, and the stay time of a job. Moreover, the correlation between the nodes and the job can also be obtained from the UG metrics. Based on the number of metrics and the collection interval, the 476 nodes cluster generates approximately 1.4 times 10 power of 7 individual data metrics per day. That's a huge amount of data, and if the data are stored in a traditional SQL databases, it will take a lot of time to produce usable results through complex queries. In order to achieve high usability and scalability from storage module, we choose the open source time series database InfluxDB as the main storage component. Also, InfluxDB contains a variety of features that can be used to calculate aggregation, roll-ups, downsampling, etc., which makes the data process more efficient. Moreover, it is also important that the schemas should be carefully designed. In our experience, the database schema plays a vital role in the performance. Here, I list two examples of the schema. First one is the fan speed metric. This data point records the fan 1 speed on the node 1.1. This is the data point recording the correlation between the jobs and the node, which shows that these two jobs are sharing the 1.1 node at the same time. Our next module is Metrics Builder. The Metrics Builder acts as the middleware between the database and the visual analytics, which hides the details of querying the database. It provides a unified API for data analysis consumers. Metrics Builder also uses concurrent processing to speed up retrieval of monitoring data. By decoupling data acquisition and data analysis, it greatly improves the flexibility and structure of the monitoring system. The main workflow is as follows. On the client side, user calls the Metrics Builder API with a set of parameters, including time range, time interval, value type, if the return data is compressed or not. Additionally, user can optionally specify the target nodes and the metrics the user is interested in. These requests will be sent to Metrics Builder. Metrics Builder first checks the requested target nodes with a valid node list and only process those nodes that falls into the valid node list. Then it generates appropriate InfluxDB query string based on the specified parameters. Metrics Builder concurrently queries the InfluxDB and waits for responses. Once Metrics Builder received the data, it then aggregates and pre-processes the data and builds the data in JSON format. It also decides whether the return data need to be compressed or not. If the user specifies a compression option, it needs to compress the data and then send back to the data analytics. Otherwise, it sends the data directly to the visual analytics. Here, I use a video clip to briefly show the interface of our data visualization tool. The node status is represented by the radar chart. We perform k-means clustering for the computing nodes, In our example, these computing nodes are clustered into 7 groups. Moreover, we can choose to show the previous status. The status is visualized in a timeline, showing the changes of the status of the computing nodes. User can hover over one node, detailed metrics will be shown. The correlation among the users, the running jobs, and nodes are also represented by the linked line. If you hover over on the jobs or the user names, the related nodes will be highlighted. In addition, we also provide grouping the nodes by their similarity. Well, this shows the node status in a more concise way. For more information about the visualization tool, please visit this website. With these modules being presented, in the following slides, I will share some experience in optimizing the performance of the monitoring system. In our preliminary design and implementation, a matrix builder required an unacceptable waiting time to query and process data from InfluxDB. This figure shows the data query performance at different time intervals over different time ranges. In general, time increased along with the time range at the same time interval. In our experiments, even the shortest time was about 50 seconds, which indicates that Matrix Builder is not a responsive service. We use a polling-based mechanism to query metrics, and we found that querying BMC-related data takes almost 80% of the total running time, and querying the UG data takes more than 10% of the time. These queries account for about 90% of total running time. Therefore, if we can save querying time, we can achieve significant performance improvement. We then explored the following optimizations to improve the performance. To improve the query performance, an intuition way is using a faster storage. Thus, we have our first approach. Switch from hard disk drive to solid state drive. We migrated the data to a host with SSDs, which provides around 391 megabytes per second of I/O bandwidth, nearly 4 times faster than HDD. However, as shown in this figure, the performance gains are limited, which is roughly 1.5 times to 2.1 times faster. Our next approach is optimizing the data schema. We also try to discard some verbose metadata and to use integer epoch time instead of strings to represent date information. This strategy results in 72% reduction in data volume and gains 1.6 times to 1.76 times performance improvement. In addition, we investigated to improve performance by taking advantage of concurrent queries in InfluxDB. We achieved 5.5 times to 6.5 times performance improvement from concurrent querying, which shows that concurrent querying is another vital technique to design in the monitoring system. This figure summarizes the performance improvements using the above approach. Overall, the proposed strategies allow Matrix Builder to perform 16 times to 25 faster than the preliminary implementation. The query and processing time was as low as 3 seconds when querying 6 hours of data. During our experiments, we also encounter another performance issue. That is, when data analysis invokes Matrix Builder remotely, the response time is still long, especially when obtaining long-range data. From the figure, we can observe that when querying long-range data, the transmission time is much longer than the query and processing time. This observation motivates another optimization, transmitting compressed data. This figure shows the total response time and the data and time distribution. Attributing to the compression, the overall performance is about 2 times faster than transmitting uncompressed data. We conclude and briefly talk about our future work in this slide. In this talk, we present the architecture and design details of an out-of-the-box monitoring tool, MonSTer. MonSTer utilizes the Redfish API to retrieve sensor data from the BMC on each computing node, and the resource manager for job information and the resource usage data. It introduces no overhead on computing nodes and only negligible overhead on head nodes. It processes the monitoring metrics and saves data points into a time series database in InfluxDB. We also developed a dedicated analysis and visualization tool, which consumes data from the provided API. Also, we have implemented several performance optimizations. The user-level information and node-level metrics can be visualized in near real time. However, as MonSTer relies heavily on existing infrastructures, and therefore the metrics collected and the frequency of monitoring time are limited by the capabilities of these infrastructures. Due to these limitations, MonSTer cannot retrieve all metrics within seconds. Regarding our future work, we are planning to collect more metrics by using additional instrumentation, and we will also benefit from the upcoming telemetry model, from which we can obtain much more sensor data at a much finer granularity. In addition, as we collect new metrics, this data analysis tool is also need to be upgraded. That's all my presentation. Thanks for your attention.